All right, to resume, I was talking about Avogadro's number and relating it to the expression for thermal energy. Uh, and there's a subtlety here, and this is why I stopped, because I wanted to gather my thoughts, actually, because there's a little source of confusion here I wanted you to be aware of. I was just saying that the problem that we were trying to solve was with this expression of 3 halves NKBT. So the value of Boltzmann's constant was known, but the ability to calculate the thermal energy contained in a substance in a sample of gas depends on your ability to determine the number of atoms or gas particles anyway that you have in your container, and that's not easy to do. And so we were looking for an alternative, and I suggested the alternative was to use this concept of moles. And so what's a mole? A mole is a measure of the quantity of some substance that you have, the quantity of gas that you have in your container. And it's defined as the number of particles. One mole is defined as a mole is a quantity of substance that has the same number of particles that 12 grams of carbon-12 has in it. And that number, as I said, turned out to be this. So here comes the confusion now. This is the number. This is Avogadro's number right there, okay? There is a very, very closely related concept to Avogadro's number, and it's called Avogadro's constant, which has this number, but it also has units associated with it. This is just a number, no units here. So this is Avogadro's constant, okay? I'm sorry, this is Avogadro's number, but Avogadro's constant is this. And I just experienced a terrible moment of doubt that I might desperately, have terribly reversed the meanings of these things. So I'm going to pause the recording and check my sources and make sure I know what the heck I'm talking about. So I'll be right back. Okay, phew, yes, I had it right. Okay, so this is Avogadro's number. Okay, just a pure number with no units. Avogadro's constant, on the other hand, which is given the symbol n sub a, reasonably enough, is defined to be 6.022. By the way, there's more decimal places than this, but this is all we usually need. 10 to the 23rd. And now, I started to say this earlier, I'm going to write a rather peculiar set of units. Particles per mole. Okay, so an amount of substance, 1 mole of a substance is 6.022 times 10 to the 23rd particles per mole. Okay, and you'll notice, and if you didn't notice, and let me make sure you notice, that I wrote particles in blue. Why did I do that? The reason is the particles right there is not actually a unit. It is an English word, but it has no mathematical existence. Okay, so what happens is that when you use n sub a in calculations, particles is not actually part of your calculation. I put it there just so you would know what I'm talking about when I start calculating with things, but it's going to disappear when we actually start canceling units out. So let's see how this becomes, well, useful. Suppose I have two moles of gas. How many particles of gas do I have? Doesn't matter what the gas is. Okay, so we have n is equal to little n is the symbol we typically use to represent the number of moles. Okay. So actually, let me write that there, I guess. So the number of particles we have, that's n that I was using over there, is the number of moles of particle we have multiplied by the number of particles per mole, which is what Avogadro's constant is. Okay? And so this is 2 moles times 6.022 times 10 to the 23rd particles per mole. And as I just said, the word particles doesn't actually appear in the math, which is good, I guess, because the moles divide out and the number of atoms just works out to be 12.044 times 10 to the 23rd per mole. Okay. God, I'm sorry. It must be late at night. I mean, the mole's canceled. We have that many particles. I'm sorry. It is. It's late on Friday night, and I'm starting to get tired. So this isn't going to last much longer. All right. So we end up with 12 times, basically 12 times 10 to the 23rd particles of gas in our container if we have 2 moles, which I think you'll agree is a respectable number. Okay. All right. So that's the relationship I needed, because now what I'm going to do, let's come back here. And I started doing this before, and so I said, okay, thermal energy is related to the temperature of the gas, sure, and it's related to the number of particles you have. That's what we've just been fiddling with, and so they're proportional to that. Here's Boltzmann's constant, 1/2. It's the same 1/2 that we used when we got 1/2 mv squared, but there's 3 spatial directions, so 3 components of the velocity, so 3 factors of 1/2 mv squared. So that picked that up. Boltzmann's constant. There's all this. So knowing n is hard, so a better approach. We just defined Boltzmann's constant, so we'll use that as our better approach. I just pointed out that we can calculate the number of particles by multiplying the number of moles of the substance that we have times Avogadro's constant, which, by the way, I don't want to conceal anything from you. What I've done now is shifted the problem from figuring out how many particles of gas we have in our container to figuring out how many moles of gas we have in the container. And this is only useful if we imagine that it's easier to figure out the number of moles than it is to figure out the number of atoms. Well, I doubt you'll be surprised to learn, yeah, it's much easier to figure out the number of moles you have. And we can discuss that in class. But in any case, for my present purposes, we'll just accept this. And so substituting that in, I get that the thermal energy then is equal to 3/2 times the number of moles times Avogadro's constant times Boltzmann's constant times T. Okay, that's fabulous. It's getting more and more exciting by the moment, isn't it? I will notice, though, that N sub A has a constant value. K sub B also has a constant value, and so that combination itself is a constant. And so I will, just for convenience, why should I multiply that constant out every time I use the thing? Let me define a new constant. Call it R. I don't know why it's called R, but why not? Anyway, Avogadro's constant times Boltzmann's constant. That numeric value is 6.022 times 10 to the 23rd per mole. I'm going to write this as mole to the minus 1 power. No, I'm not. I'll write it as 1 over mole. 1 over mole. I remember particles doesn't come into it. Okay, the word particle is just a word. Okay, Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. And so you do this, the 10 to the 23 and the 10 to the minus 23 cancel out, so you just have 6.02 times 1.38, and you come up with 8.31, and you work out the units, and we have joules over mole Kelvin, okay? And so I can replace this thing here with just R. And so my thermal energy expression has simplified down quite a bit. 3 halves N times R now times T. And if that's starting to look familiar, good for you, okay? And yeah, so we're getting somewhere. Now, I'm not going to play coy. The reason I said this might probably start to look familiar to you is because there's something perhaps, probably you've learned it back in the dim and misty called the ideal gas law. It was PV is equal to nRT. Clearly, I've got nRT over there. So 3 halves PT is thermal energy, apparently, something like that. That sounds like a question and issue to explore in a later lecture. For this recording, I think that's it. It's late at night. That's a good place to stop, and I'm tired. So I'll see you next recording.